All right, the examples that we want to go over today of logarithmic equation, or using logarithms to solve exponential equations, are when we have variables on both sides. Okay, these are going to be the most complex that we've seen. All right, but the overall process is always going to be the same. So we can do a couple of these. Hopefully, that gives us a tool to use to mimic other problems. Okay, so just like all the others, we have to isolate the algebraic part, or the variable part, which is already done on both sides. And now we take the logarithm on both sides. So add the word log here, and you add the word log there, right? Okay, so the way that's going to look is log of 5 to the x plus 1 equals log of 7 to the x. What do you do next? What do we do next with those exponents? Good. Okay. So exponents go out in front of the log. So now, because this one is a sum, we could do the same thing with this one, even though it's not a sum. But if they're sums, you're going to want to put them in parentheses out front. I don't do it, but it's not a bad thing, no matter what, to put them in parentheses, so that when they do become sums, you never forget to do that. But this is going to be x plus 1 out front of log 5. And then the right-hand side is going to be x log 7. All right, so let's draw a comparison real quick. We're just going to see if we can help realize what we're supposed to do next. And this is where, if I ever get stuck algebraically, because the algebra here I think is a little bit abstract because of the symbols that are being used. Log 5 being a symbol for another number. So log 5 is 0.7. Let's just say 0.7. So we would have x plus 1 times 0.7 equals. All right, so log 7 is 0.8, okay? Or approximately 0.8. So we have x times 0.8. Now, that is, so this, what I just wrote over here on the right, is the approximated or estimated values of these, right? Okay, so they're rounded. If I have, I'm going to rewrite this in a little bit more of a cleaner way that we would be more used to, okay? One at u, so 0.7 and x plus 1 are being multiplied together. So could I write them this way? Yes. 0.7. And then 0.8 and x getting multiplied together, you would usually write that as 0.8x, right? Okay. Can you tell me what you would do if you had this situation? What would you do next in order to eventually, you would distribute? Good. So you're going to take that 0.7 and distribute that through there, right? But working our way back to this thing, 0.7 was the log of 5, right? So let's distribute that log of 5. So I take x times log of 5 and gives me x log 5. Now I'll take 1 times log 5, so this gives me plus log 5. Equals then x log 7. So this is going to be 0.7x. If I actually did it over here, 0.7x times, or plus 0.7 equals 0.8x. Now what would you do? If you're down here, combine like so. So in order, because I got x's on both sides, right? So are you going to move, and it's up to you, are you going to move that to that side, or are you going to move 0.8x to that side? Okay, so if you want to move, so if I subtract 0.7x from both sides, working back to what their exact values were, it'd be moving this thing here, right? The x log 5. So I'll subtract x log 5 from here and subtract it from over here. Okay, so now I have log of 5 on the left equals x log 7 minus x log 5. If I'm doing the rounded values over here, it'd be 0.7 equals now 0.8x minus 0.7x. Now, most people, and I'm doing this just to allow us to see what we're supposed to do with the exact values. A lot of people, when you subtract 0.7x from both sides, are you going to automatically take and get yourself or generate 0.1x? Is that what you're going to do? Okay. But I want to look at why you would do that. Why would I make that 0.1x? And it's because you're combining like terms. And I wish things were taught this way because it would make this stuff so much easier for you to navigate through now at this stage of your math careers. But do these both have an x in them? So really what allows us to combine like terms is the fact that if I take that x out, if I factor it out, now I'm subtracting these two numbers, 0.8 and 0.7. And what does that give you? Gives you 0.1, right? And then you can multiply that together and get 0.1x. The reason I do it that way is because right here, that's how you have to do it. Okay? What do these both have in common? They have the x in common. So just like this stage right here, I'm going to factor that x out. And it's going to leave me log 7 minus log 5, which in our problem we wrote as 0.1. Okay? But I don't know what log 7 and log 5 are. They're irrational numbers, so I don't want to write them as 0.1. I don't want to merge those. Does that make sense? Okay? If you wanted to, you can maybe merge them as because it's subtraction, so you can make that maybe log of 7/5 if you wanted to, but we don't need to. But now the left-hand side is log 5. Okay? What is the end goal of every equation? To solve for what? Solve for x. How are these two things, x and log 7 minus log 5, how are those two objects stuck together right now? What operation? Multiplication. Can I undo multiplication? Okay, so I'm going to divide. I'm not going to divide by x. I'm going to divide by this thing because I want to get x by itself. So log 7 minus log 5. That cancels with that. And what I do to one side, I have to do to the other. So I'd have log 5 divided by log 7 minus log 5. And that will give me x. When we work with equations and we're trying to use exact values instead of estimated or approximated rounded values, I think it makes sense to actually find the estimated values and generate an equation that would look like what we're trying to do, but using estimated values. And if you can walk yourself through how you would do it with the estimated values, then parallel that back to doing it without rounded values or estimated values, it might make the process seem simpler, okay? And my argument is, because people always ask, well, this is really hard to do. I've never done this before. You have 100% absolutely done this before. We've done this a lot, okay? They just didn't have words in it, okay? Like log or symbols that stood in for other numbers other than the variables that are already there. Let's see if this can be checked. So I'm going to write this as log of 5 divided by log of 7 minus log of 5, okay, which is that number there. Or we could have written it this way, because if we have subtraction, we can change that into division. So I could have, if I wanted to, written it this way. Is that the same thing? Okay. And there's even some other things that we can do. Eventually, I just want to show you that there's options here. You don't know how to do this yet, and I don't know if I'll show you this later, but we should be able to take this to be, if I just want one log to show up, I can make the base this 7/5. See if I can do it. I don't know if Desmos will let me. Uh, 7/5 as a decimal is what, 1.4? So let's change it to 1.4, and then I can put 5 there. Is that the same thing right there as what this is saying? Okay, so there's a couple different ways we can write this, but if you guys write it as this, that's perfectly fine. Okay, but now what I'm going to do, I'm going to take the original 5 raised to the x plus 1, but now this is x. So I'll say that number plus 1. Okay, so that's the left-hand side. Does that give me the same thing as 7 raised to the x, which is now that number right there? Are these two things the same? Pretty close, right? If I call this one A, now the only reason that they're different, call that one B, to see if that there is a difference, we can go B minus A, or A minus B, and I don't get 0, but I get 7, a decimal point, 7 zeros, and then 6, right? So these are the same to 7 decimal places. And the reason that they're not is that because that number right there is rounded when I type it in there. So close enough for our purposes. This is the exact answer. Is that okay with everybody? Okay. And this is all based off of, like, if I'm on the ACT, or maybe I'm on Math Excel. Math Excel maybe only wants the decimal, okay? So I showed you some examples yesterday where we wanted the log of 5 over log 7 minus log 5, right? If they don't want that expression written in, but they want maybe something, they want an answer like 3 decimal places. Let's see if we can do this problem without any of the log information, but be true to 3 decimal places, okay? So I know that 3 decimal places would be that number right there, 4.783. Let's see if we can use enough decimals in our problem to get that answer, okay? So what I mean by that is once we apply our log rules. Whoa. Just get that out of there. Maybe. Once we apply our log rules of putting this x plus 1 out front, log 5 equals x log 7, okay? We can go ahead and say, okay, well, what is log 5? It's that number right there, okay? So it's x plus 1 times 0.69897. Okay, now I want to be accurate to the 3rd decimal place, so that's why I'm going out more than 3. I should probably go out 5 or 6. So that's fine. Okay, equals then x, and now log 7. See what that is? 0.845. 0.84509.8. Okay, go out several decimal places there. Okay, when I multiply this through, when you distribute that, you get 0.69897x plus 0.69897 equals 0.845098x, right? Is that okay with everybody? Okay. Now, is that a normal equation, just like we've always dealt with? Just ugly coefficients, right? Okay. So let's go ahead and take these over. Let's take those to this side. So I'm going to start with 0.845098, and we'll subtract 0.69897. It gives me that number right there. 0.146128. 128x equals 0.69897. What would you do to both sides now? Divide by that number there, right? Divide by that number right there. And it leaves me x, and now we just got to figure out what the quotient is. So I'm going to take 0.69897 and divide it by 0.146128. Does it give me, let's delete some of this stuff so you see it. Does it give me the answer? I mean, it goes out, so that number, and so which ones are different? So 2727, so that one and that one are different, right? Okay, but we're exact out to the, so this is a tenth, hundredth, thousandth, 10,000th, 100,000th place, right? Okay. So if they want a decimal approximation, maybe you don't even have to deal with the word log in the equation. Does that make sense? And that might make it easier for some of us if we have that alternative approach. That's maybe the way I would do it. Like if I got to an ACT or some type of like maybe college entrance exam that's multiple choice, and they have my answers like log of 5, like option A is log of 5 over log 7 minus log 5, and I have to find the answer that way. What I would do is I would find the answer using approximated values, and then I would go to A, B, C, and D on the test and type those into my calculator and get those values. Does that make sense? And put them in decimals. And now I compare my decimal answer to their decimal options and pick the one that's the closest. Okay? So those are all test-taking strategies, tools that we can use to manipulate our procedures to make things easier for us to get the answer. If we forget all steps, okay, we're on a test, not sure what to do. Can I always go 5 raised to the x plus 1 and 7 raised to the x? Okay, and then when I got to find where they cross, and so it might be hard with these exponentials. I might zoom out quite a bit to see where they cross. So I'm looking for where the green one ends up being to the right of the purple one. Getting closer. Well, what was the solution? Was the solution negative? That might be my issue. What I'm trying to show you is that when we click on this, and this is, I guess this might be a situation where I can't do it on Desmos because I have to scroll. So when we click, you guys remember seeing like something like 2x and x squared, and seeing where those two things cross, we can click, and it's going to give us that point, right? Okay. But when I scroll away, you see how that point disappeared? Okay. So I don't think, just because of where I have to scroll over to do that. Let's see. Let me just see something real quick. Log. Yeah, 0.69897 divided by 0.1461284.7. So the x value is 4.78. So if I go 5 to the 5.7, I got to get up to, a pretty large number here, 10,000 on the y-axis to actually see this intersection. So maybe I've got to. So I don't know. What I'm showing you here is I don't know if this is maybe the best strategy. So 10,000. So let's go the y-axis to go steps above 1,000, and we'll let this go by steps of 1. I still didn't do it. But now you see this is kind of where I got to zoom in real far. Green is still to the left of purple. This kind of stinks. I don't know if you there we go. So I got to click. So in a situation like this, I got to click and hold, or if I just click, it just kind of disappears. I got to click and hold, and that 4.732 is the answer, right? It's kind of hard that way. If you do, and I know you guys aren't maybe GeoGebra people or use it very often, but I can do the same thing in GeoGebra, but it's easier. So you've got tools out there that can help with this. If I type in 5 raised to the x, no, this is free. 5 raised to the x plus 1, and 7 to the x. Okay. What I like about this, I don't even need to look at the graph. I can. I'll go to standard view here. It shows me the graph, put my axes in. Okay. But what I can do is there's an option here. You see where I click this button and I go down to where it says intersect. I usually click on that and then click on that. Well, for whatever reason, I've never seen it do that before. So, as always, something always comes up. Yeah, it just doesn't give me that answer. It is 4.732, but I don't know why. I don't know if I've never seen. It's never done that to me before. Let's see if we could type it in. It did. Let's go. If I write it as y equals. Huh. Well, never mind. So I was just trying to show you that there are tools out there that you may have access to that could help. But graphing, I think that application shows you, because people always say, well, if I can always use a calculator to graph it and get the answer, because it's just the x value where the graphs cross, why don't I always use that? Why do I have to solve it? I think that's a perfect example. It shows you, one, the graph will give you the answer, but unless you know how to use that tool really well, you might not be able to find it real easily. Okay? And if you don't know how to do it by hand, you might not be able to know where to look on your graph. Okay? Or you see in the GeoGebra that the graph technique did not work for us. Okay? The program didn't know what was going on. So there is a benefit to always being able to do these things by hand, even though there's technology out there that can help in some instances. What if I had a problem like this? What if we went, what if I went 4, we'll just do an easy one, 4 to the 2x equals 16, let's just say 16. Okay, so you're saying, so you want to go off the same basic procedure. That's fine, because that can be done. So we know that 4 to the 2x, if this is 16, we can write that as 4 squared, right? So we're going to write the equation 2x equals 2 because we look at the exponents. And what would x be? X ends up being 1, right? Okay. Let's see if we can, let's say we forget how to do that. Okay. Can I take the log of this side? Log of 2x. Take the log of the right-hand side, log of 16. What am I going to do with that x? All right, I'm sorry, I wrote that wrong. It's log of 4 to 2x. What am I going to do with that 2x? Bring it out front. So I get 2x log of 4 equals log of 16, right? I'm going to get that x by itself. Divide by 2 log 4. 2 is going to cancel. Log 4 is going to cancel. So over here, divide by 2 log 4, right? So your x equals log of 16 divided by 2 log 4. This technique told me 1, right? Anybody know what that number right there is? That number is 1. Okay? If we go type that into our calculator, this would be the best way or the easiest way. We could do some property stuff to manipulate this and see that as 1, but I don't want to get into that. So you log 16 divided by 2 log 4. Is it 1? Okay. So what I'm trying to get at there is if you forget the like base procedure, what we're doing right now will always work no matter what. Does that make sense? Okay. So it's kind of a catch-all procedure, a safety net, if you will, to be able to solve exponential equations. What if I did something like this? I'm going to, one more example and we'll be done. What if I gave you 2 to the x plus 4 equals 13? How is this different than anything we've done so far? Say that again. Okay, so I think what you're going on would be okay if this was a multiplication sign. We haven't seen anything with addition here, right? They've all been like 2x or 2 to the x equals maybe 9, right? How can I get this to look like that? Yes. Subtract 4 first. And now I get 2 to the x equals 9. So before you can take the log of an exponential the variable term, which is this right here, has to be isolated. It has to be alone. Okay? That makes sense? So you have to get rid of that 4 before you employ the use of a logarithm. Okay? I think what we're going to do, you guys getting tired of doing this stuff? Last 3 days doing this exponential? Yeah, 38 more days. Yeah. Yeah. Actually, you guys got 45 because you guys are not seniors, right? I did that 38 for seniors. You got, and I think there's like 13 or 14 2-hour delay and 3-hour delays in that span of time. So we're getting close, getting to the end. We've been doing this for 3 days. Okay, we've been doing exponential equations. tomorrow I want to start doing logarithmic equations. Okay, so it's the inverse procedures. Okay, we'll spend a couple days on that, and then my goal is, or my thought is, to after this just jump around to topics that I think are going to be useful for you as you go to your next math class.